You joined right after your meeting. My apologies. So this is your second year.
First year.
First year, I gotta keep on messing it up, okay. Your first year at UCLA, one of the things for everyone else that, for those of you in the room who don't know, there is, UCIPS is sort of the joint efforts of a bunch of different UCs. There's UCLA, UC Berkeley, UC,
Davis.
UC Davis, and UC Merced. Irvine, all of whom do really cool transportation work, and these are collaborative efforts. We are really hoping to encourage more inter-UC collaboration in transportation. So with that being said, Youngseo, please take it away with your presentation. Thank you.
Thank you. Thank you for the introduction.
Sorry for my mistakes.
Hi everyone, my name is Youngseo. I'm assistant professor at UCLA Civil and Environmental Engineering. Today I'm going to talk about decision making in smart mobility network integrating supply. So I will start by explaining how I envision smart mobility system, and then I'm going to persuade you why is it important to integrate supply and in strategy consideration.
Sounds good.
So you may all heard about keywords like mobility as a service, mobility on demand, connected and autonomous vehicle, and aviation mobility. To put them together, we loosely define it as smart mobility system. And in this system, there are multiple agents having different objectives. So for example, governments try to achieve more sustainable and equitable transportation options. Mobility service provider try to find the momentum for growth, and travelers try to find more affordable, faster, and more convenient transportation options. So, so far, we've been focused on self-interested agents, and we usually take a particular perspective of the agent and then solve decision-making problem. But what I envision is integrated decision-making that can reconcile the conflicting interests of multiple stakeholders. So ideally, what I want to achieve is a mobility system that is good for all. All means considering all different stakeholders, and good means to help them to achieve their own goal. But although this, I know it sounds too ideal, but after this talk, you will see that how all of my research is going towards the same direction, achieving mobility system that is good for all. There are multiple sources of complexity, and one source of complexity is coming from the complexity in competition situation. So if you think about modeling group behavior, this is actually more complicated than modeling individual behavior. For example, companies compete with each other to gain more market share for their profitability, and travelers compete in a capacitated growth. And another source of complexity is coming from the strategic interaction among multiple stakeholders. So travelers try to maximize their utility. Mobility service provider maximize their profitability. Government cares about the journey. And there are two leading decision makers who are government and mobility service provider. So mobility service provider decides service availability and price. And government design and construct infrastructure system for travelers. And government and mobility service provider interact with each other through taxation and regulation. So in this system, who has the final say? This is really the travelers who make the final decision because they decide which transportation options to take. And which affect market share related to the company's profitability. And also their aggregated travel patterns affect social externalities like congestion. So there are three challenges achieving mobility system that is good for all. First is the fact that human behavior is complicated. And we don't yet know the exact impact that smart mobility system will bring to our society. And the second challenge is coming from the strategic interaction among multiple stakeholders that I mentioned earlier. And the third challenge is coming from the inherent complexity of the network environment. So you can simply think about the complicated real-world transportation network and all the vehicles and passenger flow within the network. More importantly, those components are interconnected to each other, which add extra layer of complexity. There are to model the demand and the supply side, there are two distinct modeling paradigms developed that has been developed separately. So on the demand side, to model travelers' behavior, discrete trace model have been used as a powerful tool, but they are typically analyzed on an everyday level, disregarding network topology. On the supply side, mathematical programming has been used as a powerful tool, but they often ignore endogenous travel demand because of the inherent complexity of the network optimization. And typical way of integrate those two modeling paradigm is to model it as a bi-level optimization problem. So you can think supply side model as a supply side decision maker as a leader, and then you can take demand side travelers as a follower, and then you can keep iterate those two problems until we reach to a convergence. But oftentimes there is no theoretical guarantee of these convergence. And this problem, this structure is hard to solve, both analytically and numerically.
This is more for everybody and for me. We want to save some of the questions to the end, but please feel free to ask some clarifying questions, especially if you don't understand what's going on, because sometimes these things can get a little bit complicated. Right. I know I feel that way.
Thank you. What I want to achieve is to bridge the demand and the supply side by integrating discrete trace model into mathematical program. And my unified model has three characteristics. One, it can consider complicated human behavior. Second, it considers network complexity. And third, it considers multiple stakeholders within a single model. In terms of research tool to model travelers' behavior, I use discrete trace modeling. And to model the supply side decision making, I use optimization and deep and reinforcement. Organization of today's talk will be divided into three pieces. So along the planning horizon, from short term to long term, I'll cover real-time operation, and I'll move on to the technical policy development, and then I'll finish this talk by explaining long-term planning. And I'll introduce a total of 3 of my research projects as a separate research problem because it has own application and motivation. But after this talk, you will see that how all of my research is interconnected to each other. Do anyone have any questions? If not, I will deep dive into the first topic, which is about operational efficiency of mobility on demand. So in this topic, I will take a perspective of mobility service provider, where they are considering travelers' preference, which is known. So motivation here is emerging on-demand pooling service. So you can simply think about ride pooling services like Uber Pool, where passenger can share rides with others, if they share destination. And there is another service called microtransit. You can think it as a service operated by public transit agencies, where they use shuttle van or minibus to improve accessibility to nearby transit stations. So those on-demand pooling services have many benefits because it can reduce vehicle miles traveled while serving the same amount of passenger, and also it can complement the fixed line transit. So I was a part of the large team conducting pilot operation in real city in the United States. So this project has been funded by NSF and DOE, and I was part of the Cornell team. We are collaborating with Vanderbilt University, and many private and public company has been engaged in this project. So collaborating with King County Metro, we operate microtransit system in Kansas City in Washington. And also we operate paratransit service in Chattanooga area. And throughout this process, I learned that how is it important to develop efficient operations algorithm for mobility on-demand polling, and this is really the key for the successful adoption.
At Vanderbilt, this is like Abhishek duty.
Yes. So to explain how it is happening, what is actually happening in the backend engine, I will explain what is happening after we are receiving the real-time request. We apply batch processing technique, which means that we are solving the similar optimization problems every few seconds. And in one batch, we have centralized online planner. We solve optimization problem, and then we are observing the real world reaction. And the centralized online planner, we have the core algorithm finding the best passenger vehicle matching and what is the best routing for the vehicles. And although this talk, throughout this talk, I will not explain, I will not focus on the routing parts, but our algorithm indeed has a feature to decide what is the best route for each vehicle. So the input of our system is the location information of all the passengers and the vehicles. And as an output, we can decide for each vehicle which request to serve through what order in which route. And in the real world reaction, we are realizing, like we are observing what is the actual user choice, whether they accept this offer or not. And also we track the vehicle movement. And we repeat this process until the end of the day. So in this research thread, I use techniques in operations research and computer science. And I use control technique to solve the day-ahead scheduling problem for paratransit operation. And we use reinforcement learning in different products to overcome the myopic nature of real-time decisioning. And in the last project, we apply deep learning, especially imitation learning techniques, to solve optimization faster by learning from history. And in today's talk, I'll focus on one project that focused on the reinforcement learning. To start by describing what is the actual problem, if you think about designing matching and routing algorithm for ride pooling system, then this is actually more complicated than ride hailing system. And this is because if you think about ride hailing system, the estimated time arrival, ETA in short, is given as a single value. But the ride pooling system, the ETA is given as a range. This is because of the uncertainty to share rides with others. So to make this problem extra clear, let's think about the first passenger coming into our system. So when the first passenger comes in, we can calculate what is the earliest possible drop-off time. And by adding the maximum detour time, we can propose what is the range of the ETA. Say that the second passenger comes in the next moment. Vehicle may take detour to serve additional passenger. So the estimated time arrival for the first passenger will be updated. But what we need to guarantee for system reliability is that updated ETA should be within the range. So deciding what is the best maximum detours becomes important decision variable, and you can simply think it as a slack in time or flexibility to make detour in the future. But deciding the slack time is not really trivial because of the following trade-off. If you think about the case with small slack time, then the passenger probability will go up. This is because passenger knows that they will arrive soon enough. But if you think about the vehicle's perspective, then their flexibility to make detour for the future passenger will go up. And if you think about the large slack time, then it will be the other way around. So at a core, we are having new decision variable, which is slack time. And at a core, we have discrete optimization problem. Our goal is to maximize profit for a day. And we need to balance between immediate gain at the current batch and the future gain in the next sequence of batches. And to consider the immediate gain, we incorporate discrete choice modeling to estimate what is the choice probability on the passenger side. And on the vehicle side, we incorporate reinforcement learning, and this is to approximate the state value of the vehicle. So the contribution of our work is that we are the first algorithm, mobility on-demand matching algorithm that can determine the optimal flight. So just like previous approaches, applying reinforcement learning technique to overcome the myopic nature of the real-time decision-making that can decide best passenger and vehicle matching, we also apply reinforcement learning. But what we add is the choice modeling that can estimate the choice probability on the passengers. This gives us a new feature that we can decide what is the optimal side.
And can I ask, do the trip attributes also include price?
This project, you're not considering price, we're just doing machine learning, and the price will be set by this distance based for this particular project. But after second and the third topic, you will see that how we can extend this model actually including pricing.
Okay.
To move on to so we conducted numerical experiments, and we used New York City taxi data, and we compare our method with the previous approach. But our reinforcement learning approach with dynamic slack time outperformed the baseline. And you can see more extended numerical research in our full paper on archive. And this entire framework is especially meaningful because we are effectively connect system level analysis with the individual level analysis. What I mean by that is, say we have system level decision variables such as maximum detour time and the price, and we can analyze what are those impacts, like how do service quality impact on individual level choice probability. And you can take this entire framework as a simulation, and then we can use it to design the policy. Do anyone have a question on the first one? I'll move on to the second topic, which is company travelers equilibrium and policy design. So in this topic, I'll take a perspective again as a mobility service provider, and I'll model the dynamics between travelers and the service provider. And then afterward, I'll talk about how government can use our model as a policy design. So the motivation of this research is emerging transportation network companies like Lyft, Uber, and there are some ongoing discussion whether it is beneficial for our society. Advocates said, it's complement the public transit and it reduced the dependency on private vehicles. But some critics said, although it's actually competing with public transit and it increased road congestion. To maximize the benefit and minimize the negative externality, government need to design policy design for building regulation and taxation strategy. But traditional microeconomic approach is not enough because they are often ignore network topology and also dynamics among multiple agents. So here is the complicated dynamics among multiple agents that I want to capture. Since our problem is too challenging, let's focus on a special case considering a single company. But single company can operate multiple services, so you can think about Uber monopolizing the ride-hailing market, but they provide multiple services like Uber X or Uber XL. company decide price for their mobility on-demand services to maximize their profit. And at the same time, they decide what is the best routing strategy, considering the travel time in the congested. And these related to their operation costs, which again affect their profitability. So as a reaction, when the multiple services are given, travelers can choose one of the options that maximize their utility. They also consider travel time in the congested roads. And travelers' decision affect market share, which again affects companies' profitability. And then company need to revisit their decision on pricing and route. And they repeat this process until they reach to a certain point where a company cannot increase their profit by switching their decision. And we define it as company travelers equilibrium. So the novelty of our research is that we can characterize the equilibrium of this multi-agent game that is seemingly intractable, but we formulate it using tractable convex graph. So we are connecting game of travelers with the profit maximizing company.
And with very quick, with the traveler game, do you have the opportunity to add a cost for switching companies?
Oh, opportunity cost to switch.
Well, like if there is an matching how they may operate a little bit in the real world, there's going to be a higher perceived cost. Somebody who's used to taking Uber all the time, probably gonna be a pretty low addition for them to open the Lyft app and consider Lyft as an alternative, but there's gonna be a much higher perceived cost, and it's gonna be like a lot less likely for them to switch to the train if they're normally taking.
Right. Oh, that's a really good question. So all of those complicated
That would be under
behavior
utility.
science that would incorporate in the utility function
Okay.
right now, but I'm just assuming very simple homogeneous model is
Pure. Sure, free market.
Yeah, well, yeah, we can definitely explore those all of like adding all of this realism in the choice model.
Yeah.
So our model characterized best strategy for profit maximizing company that considering the traveler's reaction. So to give you better understanding of the solution approach, I would like to explain what is entropy maximizing principle. So though this concept is the key machinery to solve our system. So if you're familiar with multinomial logic model, if you're not familiar with, just think about it as a black box model, and it takes utility as an instrument. And utility is some quantity that we can calculate from travel qualities, like travel time and travel cost. And using this closed form function, you can plug in the quantity, what is the determinant utility here, and then you can simply calculate what is the best choice probability, what is the choice probability using the model. This is really the fact that it can express as a closed form function give us many advantages in terms of computation. But if you think about plugging in this model in more complicated optimization problem, this nonlinear constraint makes our entire problem intractable. But luckily, what we can do is to write down the optimization problem. So this optimization problem has decision variable, which is the vector of choice probability. And if you solve the optimization in the right-hand side, then this vector of choice probability will actually exactly the same as the one that you can obtain by multinomial logic. And you can show this equivalence by solving the first order condition at the right-hand side. And intuitively, it also makes sense because multinomial logic model based on random utility theory, assuming that travelers maximize their utility. And there is a concept that we are maximizing the total utility. Also, we are assuming in the multinomial logic model that error term follows the number distribution, and this uncertainty can be captured by this specific term. And we also have the constraint ensuring the probability or sum of two. And this uncertainty term turns out to have a well-known entropy function, and there is many econometric interpretation about entropy. So it can interpret as value of having choice variety, or some literature interpret it as information. And most importantly, this entropy maximization problem proven to be complex program, which give us tractability and scalability. So just to brush up your memory, why do we care about complex programming? This is because of the nice mathematical property, such as existence of the solution, and all the local optimal solution turns out to be global. And this give us, these lack many algorithmic developments, such as interior point methods, which give us the tractability and the scalability of the solution. So to summarize it, the transformation from multinomial logic model to complex optimization allows us the integration of the discrete choice model into optimization problem. So you can use this technique in many different applications, but I will give you an example using the problem that I just described. So going back to our original problem, companies maximizing their profit, considering the traveler's reaction. We are writing down, we have decision variable, which is price. And also, although we have decision variable in terms of route, I'll just focus on the pricing decision. And our objective function is to maximize profit, which is revenue minus operation cost. And the revenue can it be expressed as the multiplication of demand, choice probability, and the price. And we have constraint which model the traveler's reaction, and their choice probability is the function of price. And this F function, you can consider any types of discrete choice model. It could be multinomial model. And this problem become complicated because the decision of travelers and the company are coupled through this pricing variable. The solution idea is simple. We are calculating the inverse function of the multinomial logic model. So we are expressing the price as a function of choice probability. And we plug it into the original objective function. So we are switching the domain from price to choice probability. The objective function turns out to be convex. So we can prove that the right-hand side reformulation turns out to be a convex problem. And after solving the problem in the choice probability domain, we can use the inverse function again to calculate what is the optimal price. So our contribution is that we are the first to leverage the entropy maximizing principle in the transportation network problem. And we can characterize what is our objective function and each terms are totally interpreted. So we are recovering total utility, like the term is interpreted as total utility, and we have the term correspond to the entropy function. And we have the term which represent the operation cost. And lastly, we have profit extracting behavior of the monopolistic company. And this term is something that newly appeared in our paper, and this setting with monopolistic content. So since we have a complex model to characterize the equilibrium, government can use it as a policy design tool. So as an input, our model takes all city-related characteristics, such as transportation network, travel demand, travel preference, and the fuel cost. And an output, we can quantify all different metrics. Government can use our tool as a regulation tool. And to be more specific, I bring the case study, and we can conduct some scenario-based analysis. So comparing to the baseline solution, we can explore scenarios like what if we add transit line? What if we impose fewer costs or congestion cost? What if we regulate total police? And as a metric, we can quantify all of those metrics related to the changes in consumer surplus, market share, what is the total profit, what is the congestion level, what is the total travel time. And those metrics are related to socially important keywords like energy, congestion, and emission. So as an extension of this model, you're on the process of extending our model to multiple company situation. And we are aiming to find what is the empirical equilibrium of those companies. And private company can use our model to decide whether to enter the market or not, considering the competition in the existing market. And government can use it to design the best regulation. So our integrated framework can support decision on business model and public policy. So I'll switch gear to the last topic, which is travel demand modeling for infrastructure plan. And this is actually my favorite topic. Here I'll take a perspective of the government. And given that they're designing infrastructure, we want to characterize what is the travel demand pattern. To explain what is the travel demand modeling, this is the process of fully understanding travel demand pattern in the entire city network. So we need to answer the sequence of the following questions: where are people coming from? Where are people heading to? Which travel modes they use, and which route they take. And using transportation terminology, this is about when the origin is given, modeling what is the destination, mode, and route choice. And actually modeling the group behavior of the following the decision is complicated because when I choose the best route, I contribute to congestion. And then after observing the congestion, I might want to change the route. Also, same thing happens in mode and at the destination choice. Although this modeling is really challenging, it has many economic values. And one particular application is to evaluating the benefit cost ratio for large scale infrastructure projects. So when you think about building new roads or transit lines, then we need to evaluate the benefit cost ratio. And to evaluate the benefit, we need to predict the future demand pattern. And the associated costs are massive. For example, US government spent $55 billion on highway construction in 2023. And they spent $27 billion on transit construction. And inaccurate estimation cause a lot of social costs. For example, underestimation causes travelers dissatisfaction, and overestimation causes wasted government spending. What is happening in practice is they often use what's called traditional four-step sequential model. So as an input, they take entire transportation network and services. They also take populations and land use information. And then they model the sequence of choices. Say that the origin is given, they're modeling with what is travelers, destination, modes, route choice. Using transportation terminology, this is called as trip generation, trip distribution, modal split, and traffic assignment. And after this process, we got what is the flow on each road network. So we got the link traffic count, which is nothing but the number of cars on each road. And among all of this process, traffic assignment is the most computationally expensive process. So what people do in practice is to use software like ME4, and then this is the method to South Korea after traffic assignment. So width of the links is proportional to traffic count, and after getting the simulation outcome, we need to compare it with the observation from real world. So you can think about the data from loop detector or camera. And then there is a process of iterative adjustment of the parameter. So even for experienced experts, this process could take up to 3 months to find the best parameter set to represent the real world data. What I propose is the combined model that eliminate the needs of this iterative adjustment process of the parameters. So our model will provide more robust parameter estimate with automated calibration. And after having the combined model with the calibrated parameter, we can finally predict the future travel demand pattern after the construction, large-scale construction, after adopting innovative mobility services, after changes in demographics. So our contribution is that we are the first model to incorporate parameter calibration in a convex program. Compared to the previous approach, which takes the sequential modeling approach, our approach combines all that to connect the game of the travelers and build infrastructure. And our integrated model has potential to connect urban planning with the analysis of mobility patterns. So let's deep dive into the problem. So if you think about where the source of the challenges is coming from the incomplete observation. So since transportation network is too large and there are too many travelers in our city, we can either observe sparse and point-based traffic counts, or we can observe a full trajectory, but for a subset of travelers. So you can think of cell phone location data or smartphone data. What we want to do is to complement this incomplete observation using theory-driven model. So we are using parametric and aggregated model, which hold as hierarchical logic model. The model called hierarchical model because we are modeling the layer of choice for destination, nodes, and routes. And we are using corresponding and appropriate logic model, such as multinomial logic, nested logic, and precise logic model. But the key takeaway is that we incorporate flexible choice model, capturing rich behavior. So we propose two-stage model, first estimate and then second predict. In the first stage, we are estimating parameter and we are reconstructing current travel pattern. And using the calibrated parameter in the first stage, in the second stage, we'll predict the future travel pattern. So I will deep dive into the first stage model, but I'll skip the second part because once we formulate the first stage, modeling the second stage is mathematically trivial. To go deep into the first stage problem, our objective function is the linear summation of entropy function and Beckman equation. Entropy function, that's something that I already explained. This is correspond to the choice model, and it can capture the uncertainty of choice. Beckman equation is something that I borrow from transportation literature, and this is to capture the traffic equilibrium, considering the congestion. Entropy functions takes probability as variable, and it can form the travel pattern. And Beckman equation takes traffic counts, the number of cars on the road, as variable, and it helps us to consider congestion in the road network and travel equilibrium. So to summarize it, our objective function has a total of 3 entropy functions, which correspond to each of destination, mode, and route choice. And we also incorporate Beckman equation for traffic equilibrium in the route choice. And by modeling everything in a single model, we can consider the congestion in the route choice level affects mode and destination choice. Since we already model our objective function as a complex model, the remaining challenge is to model the remaining constraints as to not violate the complex constraint. So we need to incorporate, ensure that traffic pattern matches with the observation. So we have constraints related to conditional entropies and momentum matching. And we form it as convex inequality constraint and linear equality constraint. So our first theorem shows that our first stage model is a convex program. And by finding tonic representation and by using state-of-the-art like commercial server like SD, like Mosaic, SCS, and ECOS, we were able to apply our model in benchmark transportation network, including Sioux Falls, Anaheim, Eastern Massachusetts, and 6 more networks, a total of 9. And as we increase the network size, our solution time increase. But even at the largest case for Chicago sketch, we were able to find the optimal solution within approximately 2 minutes. So it shows the tractability and scalability of our formulation up to real world scale. And the first theorem showing that our model is a complex program. It was the second theorem. By solving KKT condition, we show that the optimal primer and the dual solution satisfy the hierarchical logic model that we saw earlier. So essentially, what the second theorem is saying is our primer solution gives us the travel equilibrium, while the dual solution gives us the parameter estimates. So it gives us the one-shot framework to estimate our parameter without iteration. And if you think about the dual problem, this is something similar to maximum log likelihood, but our problem is unique because of the additional constraint for observations. To conclude my talk, I would like to revisit what was the challenges in complex and interconnected system. First, we have complicated human behavior. Second, we have multiple stakeholders and their strategic interaction. And third, we have inherent complexity within the network. And those components are interconnected to each other. So I've been trying to bridge the demand and supply side, and we saw the benefit of the integrated framework. In the first project, we saw how behavior-aware decision-making in real-time mobility on demand can increase companies' profitability. And in the second topic, we saw how we can model seemingly intractable multi-agent game using tractable complexity. And in the third topic, we saw how we eliminate the manual calibration and automate the decision-making process. My ultimate goal is to integrate and automate the decision-making. And I would like to connect the supply and demand side. I would like to combine macro to micro. And I would like to blend the design and operational part. Lastly, I would like to thank to all of my collaborators and sponsors. I would like to take any question you may have. Thank you for listening.
Questions, guys?
Thank you very much
Thank you.
for a very nice presentation. In the last project, mode choice.
Yeah.
It's can you tell me more about it? Because mode choice, if you would be modeling a European cities versus a US city, why you needed to put mode into this framework like this?
Oh,
How do you introduce a mode choice into your formulation?
So what I mean by transportation mode is like public transit, private car, walking, cycling, and are you having the same?
Yes, because in order to have a traffic assignment problem, usually the mode can input as a variable. So you put the number of cars. Because I don't know if you can, if this framework can capture the complexities of mode choice in Berlin versus Chicago.
Oh,
Given the quality, so it's
Uh-huh.
open a Pandora box, just adding mode there in this framework. And my question is, I was wondering, is it needed? You can add it as a vehicle usage rate for the in terms of the audience.
If I understand your question correctly, so for different city, we need to we need to do this analysis for each city. So let's say Chicago. We will start with the demand of the origination,
Yes.
and then we don't need anything else, but we can reconstruct the travel pattern through this theory-based model. But we can also validate our model using like traffic count data, like TENS data, for example, like traffic count from route detector. And then we can minimize the error between simulation, like our output model output and the observed data. And then another way of validating it, or we can even consider having additional constraints like no one would share data. Like, cause like we usually we know the mode share.
So you ask the travel time in transit, in your variables.
Right. So it's like we are, what we capture is indeed is like say that there are multiple OD, like origin to demand in the entire city network. And for each OD, like it has, each mode will have different travel time. And our model can capture that level of granularity.
I have one question then. But yeah, so please feel free to jump in. More in the first topic, a little bit in the second. I'm curious if I'm trying to say it's the simplest way. Could you use the models you've developed to help identify the right areas, customers, and business models for some of these solutions? To start with ride pooling as an example, I think it's very fair to say ride pooling has been a pretty massive failure in the US. Uber tried it, Lyft tried it, they all pulled away from it. And in large part, they pulled away from it because the economics, right, just don't work out. As soon as you start pulling away the subsidies, people are not willing to make the trade-offs and within any reasonable rerouting time, et cetera, et cetera. I'm curious if you can use the models that you've had to input some assumptions to identify what opportunities there are that would make sense. And at least this is dating more back to my time at Ford. The private sector in general seems to have a really poor understanding of transportation modeling and especially transportation decisions and how people operate there. So they will frequently be running, they will make choices for their new business models that for those of us in transportation engineering, I might call out a Berkeley professor, Robert Cervero here, who did a lot of work on this in the 90s, simply don't make sense. And then it starts up, oh, great, Silicon Valley reinvented the bus type of solution. So, but I think it's fair to say, well, there are opportunities where these things would make sense. I'm curious, have you ever thought about maybe taking those models and pushing it from the other way with reasonable assumptions? What are the actual, what types of business models or services would start to make sense that people would actually want to be taking? Because cooling in urban environments does not seem to be it.
Yeah, I totally agree. That is part of the reason why I started the first project. Because as a customer, I had a bad experience using Uber Pool because they said they will arrive in time, on time, and I feel like, oh, I might not be the only one who will be in the Uber, but it wasn't. And it was such a bad experience that I cannot guarantee the estimated time.
Yeah.
I don't mind delaying because of the traffic. But if they start putting other passengers for their own benefit, as a customer, I kind of get mad. So I wanted to ensure, I wanted to develop algorithm that can guarantee the modeling principle was like they need to keep their promise. So I think there's a chance to develop more efficient algorithm, not just for their benefit, but also care about customer side. So I think that would be this attempt to consider choice probability on the passenger side will actually broaden the chances also in the business because all of their kind of analysis assume that customer will definitely accept their call, which is not the case in the real world. So I think
well, let me put it slightly different. Where I was trying to get to there is very interesting. So there was the optimization. Uber probably had a bad algorithm underlying it and it wasn't working out. What I'm also curious about though is if you made some reasonable assumptions, could you identify the types of trips and the types of services where pooling makes sense?
Right.
My hypothesis here would be in most cities, especially outside of the hyper dense ones like New York where there are other options, pooling is not going to be an attractive option for most typical trips, simply because you don't have enough aggregation of demand spatially and temporally to justify pooling. But you might be able to say, well, in major events,
Oh.
that Uber shouldn't have done a general Uber pool, they should have done Uber pool for major events, because getting to and leaving a San Francisco Giants game is exactly a perfect example, because there you do have, at least at one end of the trip, massively aggregated demand, both spatially and temporally.
Yeah, I think that's a really good example. And also, even in a high density like cities, there might be a chance that like if people are going
Yep.
to our same direction, they might take a much detour. In that case, like high capacity pooling would definitely make sense.
Yeah.
And especially if you're incorporating some like autonomous people and operating high capacity people, then it might be also make sense to operate them in the like rural area where demand might not be like not might be enough to satisfy the traditional bus system, but we can like public transit agency can operate like shuttle service that looks like Uber pool, but which is actually in the public transit system.
Mhm.
So I think those three would be the potential revenue for the self-sustaining business model.
Pooling ski resorts too. Sorry, that's you. All right, I'm not quite now. Thank you so much.
Thank you for your presentation. I have a question about traveler utility function, which can be very special at temporal context. So for example, even for the same person, it's the way on the factors like distance and travel time can be different depending on the situation. For example, in the commute, like morning commute, everyone is busy. Everyone is just busy and get to your location in the right time. So the time is the most priority factor, but like the nightline, they just, is going, and whatever, I can wait more than 5 minutes, so the time can be more, what can I say, less priority.
Right.
So can you reflect this kind of variation for those, as well as, I wonder if it is possible and worthy to make matching model customized to each individual or the group of people who has the similar characteristics to make sure make sure that as some loyal customers.
Yeah, I think that's a really interesting question. So, well, I think like modeling the group behavior is definitely interesting, especially, as you mentioned, their price sensitivity would be different by travel purpose, and it could be varied by the time, as you mentioned. So what we can extend is to, instead of having homogeneous, travel, like choice modeling, we can extend it to have like multiple group choice model. So we cannot, I don't think it's feasible to extend it to a heterogeneous model, but we can definitely have like latent group, for example, and then based on all the feature that we can observe, like time, maybe they can state their travel purpose or not, or we can even like predict what is their travel purpose, like for example, they're commuter or they're just they're going here just for fun. And based on that, we can like estimate what is the best price sensitivity and like switching like preference on each modes. And then we can incorporate it in our like the similar framework. I think that's totally possible, and we're actually working on that extension.
Hi, thanks so much for the talk. I have a question regarding the second part of the presentation.
Yeah.
It's very interesting how you reformulate the problem so you can solve it as a convex program. But my question is, I'm wondering about to what extent do you think the operational policy would derive from that problem? And, to what degree can that policy be implemented?
Right, I'll be really honest, so we're assuming static model, it's not dynamic, and I think adding dynamic, dimensions would make problem infeasible. So we definitely need like multiple model that can complement our decision, but what we can show is at least for specific time, horizon, say 1 hour, we can capture the complexity pretty well. And then we can use different model, which it could be like dynamic model, it could be other simulation-based analysis. And then using them together, I think it's like we can make better choice in terms of policy. So I think I'm not claiming that our model is perfect, but it captures some dynamics that couldn't be captured using existing model. So I think it's about like complementary relationship with other existing model.
I see, so, if I'm understanding this correctly, so the advantage is in price discovery.
Mm.
And then you can use that price in other models that actually offer the full operational policy.
Oh, so there are multiple dimensions. So for example, our model right now, as of now, we can only analyze monopolistic situation where there's only a single company monopolizing the ride-hailing market. In that case, we can use our model and also we can use agent-based simulation, and then we collectively use those information to make the final judgment on what's the best policy. But for the extension, we definitely need some theoretical extension. And then, but also in that case, our model do have some assumptions, like we are using the simplest utility function. And so like in the real world, travelers might not want to maximize their utility. They may make some irrational choice. But we are not capturing those kind of realism, and that realism can be complemented by the other existing efforts.
Thank you.
And we may need to finish it, and but I'll be here and you can ask any question you may have. And thank you all for attending.
Thank you so much. As a heads up, everybody,